In the quiet darkness of the universe, long before the first stars awakened, there was a stillness so complete that it seemed to stretch forever. Imagine yourself drifting in that ancient calm, suspended in a silence untouched by light, untouched by sound, untouched by time as we understand it. The cosmos was young, yet unimaginably vast, a sea of gentle darkness waiting for its first spark. As you settle into this story, allow that darkness to surround you, soft and welcoming, like a deep night sky that has no edges and no urgency. This is the beginning of everything. This is the place from which all stars, all planets, all atoms, and all living beings would one day emerge. In this opening moment, the universe is only a few 100,000 years old. It has expanded from the fire of the Big Bang into a cool, dim expanse, filled with hydrogen, helium, and the faintest whisper of primordial light. That light is stretched now, softened, thinned across the growing space. What remains is a universe resting after its violent birth, a universe exhaling. The temperature has fallen enough for atoms to form. Electrons settle into orbit around protons. The earliest elements gather like scattered seeds, waiting for the right conditions to grow into something more. Everything is simple. Everything is calm. As you imagine this darkness, feel yourself drifting deeper into stillness. There is no rush, no motion you need to follow. Only the gentle unfolding of a cosmic story that began nearly 14 billion years ago. The universe is quiet, but not empty. Tiny fluctuations ripple through its fabric, delicate variations in density that will guide the future. Pockets of gas are ever so slightly thicker than others, subtle enough that they appear almost identical, yet significant enough to shape everything that will come to be. These small fluctuations are like the first breaths of potential. They are the seeds from which galaxies will grow. In this vast darkness, the laws of physics lie patient and consistent. Gravity waits like an artist preparing to sculpt something tremendous. It reaches into the scattered gas, drawing atoms closer, ever closer, gathering them from across enormous distances. As you listen, imagine drifting before the birth of the first star, floating among silent clouds of hydrogen. There is no glow yet, only the soft sense of a universe preparing to create its first lights. This moment is calm, and you can feel yourself soften into that stillness. The cold, gentle dark wraps around you like a blanket, encouraging your breathing to slow, your mind to rest, your thoughts to drift like cosmic dust. The universe in this age is not hostile. It is peaceful, a quiet cradle for possibilities that have not yet awakened. With every passing million years, gravity pulls the gas into denser knots. The clouds begin to take shape, enormous and slow, drifting through a blackness that stretches in every direction. These ancient clouds are the ancestors of everything you know. They are the raw material of starlight, the beginning of every story told by galaxies, the origin of the atoms that will one day form oceans, mountains, forests, and living creatures. As vast as these clouds are, imagine them stretching for hundreds of light years, yet moving so gently that they seem motionless. Their atoms collide softly, their filaments twist slowly. All the while, gravity gathers them more tightly, drawing them toward a moment of ignition that has never happened before. This is the cosmic dawn, though no light has yet appeared. You are floating in a universe on the brink of transformation. A universe about to create the first stars that will illuminate everything that follows. Take a moment to breathe here. Imagine drifting in this deep primordial calm. The silence is soothing. The darkness is comforting. It holds you like a vast cosmic ocean, unhurried and serene. You are listening to the story of the universe preparing to open its eyes, preparing to spark its first flames, preparing to illuminate the void. The stillness continues for millions of years more. The gas clouds grow increasingly heavy, and somewhere, deep within one of those clouds, gravity tightens its grip just enough for something extraordinary to begin. You may picture it like a soft glow forming behind a veil. At first, there's no light at all, only warmth slowly building deep within the densest core of a collapsing cloud. The atoms fall inward, drawn by the relentless pull of gravity, and the temperature rises steadily. What was once cold, quiet gas is now warming from compression. At this moment, the universe holds its breath. The first star is preparing to ignite. As you float in this cosmic stillness, you can feel the sense of anticipation. Not hurried, not tense, but deeply serene, like the gentle quiet before sunrise. The universe is vast and patient. Everything unfolds at the rhythm of nature, unhurried and perfectly timed. It is in this slow gathering, this peaceful build-up, that the journey of starlight begins. In telling this story tonight, we will walk together through the entire life cycle of stars, from their gentle beginnings in dark nebulae to their brilliant lives, their dramatic deaths, and their lingering remnants. We will explore how stars shape galaxies, how they forge the elements that fill our world, and how every atom within your body was once part of a star that lived and died billions of years before Earth existed. The creation of stars is not only a scientific process, it is a poetic one, a reflection of cycles that repeat through the universe, from birth to death to rebirth again. As you listen, you may find yourself drifting into a timeless sense of wonder. The story of stars is not rushed. It moves slowly, like the unfolding of cosmic clouds. It has no urgency, no sharp edges, only gentle rhythms, soft transitions, and calm explanations that mirror the natural pace of the universe itself. There will be moments of awe, moments of softness, and moments of deep reflection. You are free to drift in and out, to relax into the narration, to let the cosmic imagery ease your mind and guide you toward rest. In the darkness before the first stars, everything is potential, everything is waiting. And now, as gravity gathers the gas clouds more closely, the first lights of the universe prepare to ignite. This is where our story truly begins, in the quiet before creation, in the darkness before dawn, in the soft, endless calm that held the universe gently until the first stars were ready to shine. The darkness deepens, quiet as a long cosmic night, and you drift within it, calm and weightless. Soon we will enter the birth of the first stars, and the universe will awaken with light for the very first time. But for now, rest in this ancient stillness. Feel the serenity of a universe yet to shine. Feel the gentle pull of gravity, drawing matter into the promise of future starlight. Feel the slow, patient breath of a cosmos preparing to illuminate itself. The silence is vast, but it is warm and comforting, wrapping around you like the memory of nights beneath open skies. Here, in this calm beginning, we take our first step into the story of creation, the story of starlight, the story of everything that has ever existed. And as we continue, the universe will glow, breathe, burn, collapse, and rise again, all in a rhythm as ancient as time itself. The dark before light. In the vast quiet of the early universe, the darkness stretched in every direction like an endless ocean of cool emptiness. This darkness was not frightening. It was soft, deep, and peaceful, a kind of cosmic night that cradled the ingredients of everything that would eventually come to be. As you drift in this ancient expanse, imagine the universe still expanding from its fierce beginning, growing larger and cooler with every passing moment, its temperature falling into a range where hydrogen atoms can form and remain stable. The light from the Big Bang has faded into a gentle background glow that is now stretched so far and thinned so completely that no stars, no planets, and no galaxies pierce the darkness yet. This era is known as the Cosmic Dark Ages, an epoch of quiet waiting. Imagine yourself floating through this age, where there is no starlight to guide your eyes and no sound to fill the silence. Matter exists, but it is spread thinly, like a fine mist that has yet to gather into anything recognizable. The darkness is smooth on large scales, but if you drift more carefully, more slowly, you begin to sense tiny ripples in the density of this primordial gas. These ripples are slight variations in how matter is distributed, shaped by the earliest fluctuations in the universe's energy. Though they appear subtle, almost imperceptible, they hold within them the seeds that will one day form galaxies, clusters, and the vast cosmic web that stretches across the observable universe. As you float through this era, imagine the hydrogen atoms drifting gently, colliding softly, cooling slowly. Gravity is working quietly, silently gathering matter in ways so delicate that millions of years pass before anything noticeable occurs. Yet the process is beautiful in its patience. Gravity does not hurry. It draws matter inward with a persistent, gentle pull, guiding the universe toward its next transformation. Over time, these small ripples in density grow more pronounced. Tendrils of gas begin to form. The earliest threads of the cosmic web stretch out, forming patterns that resemble the faint outlines of future galaxies. The darkness remains unbroken, but it is alive with subtle motion. Every atom is on a slow journey, carried by the expansion of space itself, yet tugged inward by gravity. You may imagine the gas clouds drifting like colossal shadows in an indescribably vast night. Their edges are soft. Their interiors are cool. They move so slowly that an entire lifetime of a human being would be less than the smallest heartbeat in their evolution. And yet, they move. They gather. They respond to the quiet tug that shapes the universe's destiny. As millions of years pass, the densest regions of these clouds grow heavier and cooler. The gas continues to collect, and tiny structures begin to form, fragile at first, but growing stronger with time. These structures deepen into gravitational wells, deep pockets where gas accumulates more quickly. The temperature inside these wells rises by increments so small that they seem negligible, yet across vast scales of time, they are profound. The universe is preparing itself for the first stars, though this preparation is slow, elegant, and almost imperceptible. You drift closer to one of these forming regions, and even though all remains dark, you can sense the weight of potential gathering. The gas is beginning to compress under gravity's pull. As the cloud collapses inward, it starts to fragment into smaller clumps. Each fragment becomes a cradle for something new. Within these clumps, the pressure increases. The atoms collide more frequently. The temperature rises, and the darkness begins to thicken with the promise of future light. Imagine drifting slowly around one of these forming clouds. Its edges swirl gently, shaped by turbulence in the gas. Within its core, the pressure is building. The hydrogen atoms are being squeezed closer and closer together. Though nothing yet shines, the cloud is warming from the inside. The potential for light is gathering in layers, like a spark hidden deep beneath a mountain of cold dust. The collapse continues unabated, guided only by gravity and time. The temperature must reach millions of degrees before nuclear fusion can begin, and that moment is still ahead, still rising in the future like a distant dawn. In the darkness, this collapse is the first sign of change. The universe is no longer merely expanding and cooling. It is beginning to organize itself. It is beginning to create structures. And at the heart of these structures is the quiet, steady process that will ignite the first starlight. That ignition, when it comes, will be invisible from the outside at first, buried deep within the collapsing clouds. But the heat within the core grows, rising slowly, steadily. You can imagine the hydrogen atoms vibrating with increasing energy, their collisions becoming more forceful, their movements more intense. They are preparing for fusion, the process that will define the life of every star. As time continues its slow march, the cloud becomes denser still. The core grows more compact. The atoms press tightly against each other. The warmth deepens. A protostar is forming, though its light is trapped beneath countless layers of dust and gas. You drift in the surrounding darkness, watching the cloud tighten like a colossal cosmic embrace. The darkness itself feels like it is beginning to swell with the promise of illumination. Though no light escapes yet, something inside the cloud has awakened. The temperature at the core continues to rise. If you could touch this forming heart of gas, it would feel warm, almost alive. A quiet ember hidden beneath a soft, opaque veil. The protostar gathers mass from the surrounding cloud, growing heavier, denser, and hotter. The infalling gas spirals inward, creating gentle currents that wrap around the forming star. This swirling motion creates a disk around the core, shaping the environment from which planets may eventually form. But for now, all focus remains on the growing heat, the increasing pressure. The universe remains dark on the outside, but inside these clouds, a great transformation is underway. The protostar contracts further, its core reaching temperatures high enough to change the very nature of matter. The atoms begin to move with such speed and force that their mutual repulsion is overcome. They collide and merge, and for the first time in cosmic history, hydrogen nuclei fuse into helium. This process releases light, not just any light, but the kind of radiant, sustaining light that defines stars. The first spark of true starlight forms at the center of the protostar. The core becomes a nuclear furnace, an engine of immense power. And though the outer layers of the cloud still hide this light, it is now burning. As the pressure from fusion builds, it pushes outward, balancing the inward pull of gravity. The moment this balance is achieved, the star is born. Its energy flows outward, heating the surrounding gas and eventually clearing a path through the cloud. The first rays of starlight break through the darkness like a cosmic sunrise. This is the end of the Dark Ages. The universe awakens. The first stars are immense, far larger than most stars that exist today. Their fusion burns hot and fast, illuminating the surrounding space with intense ultraviolet light. You can imagine the darkness beginning to glow, faint at first, then growing brighter as more stars ignite across the universe. The cosmic night is pierced by the earliest constellations, though no eyes yet exist to witness them. Their light travels through space, ionizing the gas, transforming the universe from a cool, neutral expanse into a warm, glowing tapestry of flickering brilliance. As you drift through this era of awakening, imagine the transformation unfolding around you. The once silent universe now hums with the energy of countless newborn stars. The gas clouds glow softly from the light within them. Galaxies begin to assemble, drawn together by gravity into rotating spirals and elliptical shapes. The darkness softens with the glow of starlight scattered across unimaginable distances. The cosmic web shines faintly, its filaments illuminated by clusters of forming stars. The universe is no longer a quiet expanse. It has become a vast, living tapestry of light, motion, and transformation. And within this expanding sea of starlight, the story of creation begins in earnest. The darkness has served its purpose. It held the universe in patient stillness until the first fires could ignite. Now, those fires burn across the cosmos, illuminating the path for everything that will follow. You drift in this new, glowing universe, feeling the warmth of starlight that stretches across the cosmic ocean. The darkness before light has ended. The stars have awakened, and the universe, once quiet and still, now breathes with radiant energy, ready to begin the next chapter of its story. The birth of a star. In the soft glow of a young universe, now awakening with light, the birthplaces of stars stretch like quiet, celestial cradles across the cosmic landscape. These regions, known as nebulae, are vast clouds of gas and dust drifting in beautiful, intricate forms. Some are faint and almost transparent, while others are dense and dark, their interiors hidden from view like secrets waiting to be revealed. As you drift closer to one of these dark nebulae, imagine its edges shimmering faintly with reflected starlight from distant neighbors. Inside, the cloud is cool, shadowed, and thick with the raw materials of creation. Within a nebula, gravity is constantly at work, shaping the future in slow, patient strokes. Hydrogen atoms drift through the cloud in enormous numbers, colliding softly, gathering, settling into regions of slightly higher density. These regions, once formed, become stronger over time. Gravity pulls more gas toward them, and the cloud begins to collapse in places, its structure growing more complex and dynamic. Filaments stretch across its interior like threads of cosmic silk, guiding the gas into long, winding shapes. Nodes form where these filaments intersect, becoming focal points for collapse. Imagine drifting within one of these collapsing regions. The temperature is low, cold enough for molecules to form and remain stable. Gas flows inward from all directions, drawn by gravity into a growing, contracting sphere. The collapse is not violent. It is slow, like the gradual tightening of a gentle embrace. As the gas falls inward, it releases energy in the form of heat, warming the center of the collapsing cloud. The core becomes denser and brighter in heat, though no visible light escapes yet. This growing core is a protostar, a star in the earliest stages of formation, hidden deep within the cloud that birthed it. The protostar's environment is one of swirling dust and gas. Material from the cloud continues to fall onto it, spiraling inward through a disk that forms around the young star. This spinning disk, made of gas, dust, and ice, flattens under its own rotation, creating a smooth, circular shape. Within this disk, particles collide and stick together, forming larger and larger clumps. Though they are far from becoming planets at this early stage, they mark the beginning of a process that will one day create entire solar systems. The protostar continues to grow in mass, drawing material from the surrounding environment. As it grows, the protostar becomes hotter. The temperature in its core rises into the millions of degrees. This heat is produced entirely by gravitational compression. Hydrogen atoms are forced closer and closer together, moving with increasing speed and energy. The protostar glows in the infrared, though the dense cloud around it still hides this glow from distant space. Its light is a whisper compared to the brilliant shine it will produce once fusion begins. In the heart of the protostar, the pressure becomes immense. Hydrogen nuclei are being pushed so tightly together that their natural repulsion begins to weaken. The protostar approaches a threshold, a critical point where the forces at play will cause a profound transformation. When the temperature reaches about 10 million degrees, hydrogen fusion begins. Protons collide with such force that they combine to form helium, releasing enormous amounts of energy. This energy pushes outward, creating a pressure that balances the inward pull of gravity. This moment marks the true birth of a star. The protostar transitions into a main sequence star, stable and luminous. The surrounding cloud begins to respond to the new light and heat. The pressure from the star's radiation pushes the remaining gas away, clearing a cavity around the newborn star. Over time, the nebula thins, revealing the star's bright glow to the universe. The cloud that once concealed it scatters into space, either blown away by the star's light or incorporated into new structures within the nebula. Imagine emerging from the dense, shadowed cloud into open space. The newborn star shines bright, radiant, and warm. Its surface glows in a steady, golden light, the result of nuclear fusion taking place deep within its core. The surrounding area is still filled with leftover dust and gas, illuminated by the star's light, creating a halo of soft, shimmering patterns. The birth of a star is not a sudden event, but a gradual emergence, like the rising of a dawn that gently overtakes the night. You drift near the glowing surface of this young star, its light warming the space around it. Fusion has made it stable. Its light will shine for millions or even billions of years, depending on its mass. The star breathes outward, releasing stellar winds that shape its surroundings. These winds carve paths through the nebula, sculpting pillars, arches, and cavities in the remaining gas. The star's presence transforms its environment, creating a new area of space that glows softly with reflected and scattered light. In many regions of the universe, star formation occurs in clusters. Multiple stars are born from the same cloud, all emerging at different stages. Some stars form more quickly, others more slowly. Some grow larger than the one you now observe, while others remain small and faint. These clusters can drift apart over time, their stars spreading across the galaxy, each carrying with them the chemical fingerprints of the cloud that created them. For now, they remain together, illuminating their shared nebula like tiny jewels suspended in a cosmic veil. As you drift through this glowing region, observe how the stars vary in brightness and color. Massive stars shine blue and white, their light intense and powerful. Smaller stars glow with a softer reddish hue, their temperatures lower, their lifetimes longer. The diversity in these stars comes from the varying masses collected during their birth. Mass determines a star's fate more than any other factor. It predicts how bright it will shine, how long it will live, and how it will eventually die. The star you are observing now may be similar to our Sun, a medium-sized star with a moderate mass. Such stars are long-lived compared to their massive cousins. They burn hydrogen steadily, radiating warmth and stability into their surroundings. The disk around this star continues to evolve, flattening further, cooling, and beginning the slow process of forming planets. Tiny grains of dust collide and stick together, forming pebbles. Pebbles grow into rocks. Rocks collide and form larger bodies. In the depths of the disk, gravity continues its quiet work, shaping what will someday become a planetary system. You drift through this disk, imagining the swirling particles slowly gathering into worlds. Some areas are warm, close to the star, where rocky planets may form. Further out, the temperatures drop, allowing ice to accumulate. Gas giants may form in these colder regions, their masses growing rapidly as they capture the hydrogen and helium that remain abundant. The disk continues to thin as planets, moons, comets, and asteroids take shape, sculpting a system that will orbit the star for billions of years. The star itself continues its radiant life. It is now fully stable, a self-sustaining engine powered by nuclear fusion in its core. Its outer layers are calm, illuminated by the light from within. The surface roils with convection, heated material rising and cooler material sinking in rhythmic cycles. These motions create patterns of granulation across its face, like gently shifting waves. Magnetic fields form and twist, occasionally releasing flares and bursts of charged particles. Despite this activity, the star remains steady, its glow constant and reassuring. Imagine drifting just far enough from the star to appreciate its full brilliance. Its light travels outward in all directions, carrying energy across vast distances. This light will journey for years, even centuries or millennia, before reaching any distant object or observer. Some of it may escape into intergalactic space, traveling for billions of years until it crosses the darkness between galaxies. Other portions will be absorbed by dust, warming it and causing it to radiate in infrared. But much of the light simply continues outward, a testament to the star's internal furnace. The birth of a star is not only a physical transformation, but a symbolic one. It represents the emergence of order from chaos, light from darkness, energy from collapse. It is a process that has repeated countless times throughout the universe's history, shaping the structure of galaxies and giving rise to the conditions necessary for life. As you drift near this young star, you feel a sense of calm and wonder. This star will shine for a long time. It will warm any planets that form around it. It will influence the motion of everything in its system. It will write its story across the fabric of space through its light. The nebula around it gradually dissipates, leaving the star and its forming planets in clearer view. The darkness beyond the nebula stretches infinitely, punctuated by the glow of other stars forming in distant clouds. The universe is no longer a place of silent stillness. It is a place of creation, of light, of warmth. As you drift through the remnants of the nebula, you can feel the energy of this transformation. From cold gas and gentle darkness, a star has been born, illuminating its surroundings and marking the beginning of a long and luminous life. Now, the newborn star stands as a beacon in the cosmic night, its light carrying the story of its birth across space. And as you drift deeper into this universe filled with glowing spheres of fusion and warmth, the next chapter unfolds, exploring the long and steady life of these magnificent stars, the engines of light that shape the cosmos, the life of light. The young star settles into its long, luminous adulthood with a quiet sense of stability, like a gentle flame that burns steadily in the dark. Its birth was dramatic in cosmic terms, a slow collapse followed by an explosive awakening, but now its life enters a calm and enduring phase. This phase is known as the main sequence, the long stretch during which a star spends most of its existence. As you drift near the glowing sphere, imagine its surface shimmering with soft waves of golden light. The star's radiance is warm and constant, a quiet heartbeat that pulses outward through space, illuminating everything around it. Inside the star, deep within its blazing core, hydrogen atoms fuse into helium in a process that releases immense amounts of energy. This fusion is the star's steady engine, the power source that allows it to shine. The pressure from fusion pushes outward with just enough force to balance gravity's inward pull. This perfect equilibrium is delicate yet stable, and it defines the life of a star during this long Middle Age. Imagine the core as a radiant sphere within the star, glowing with light that takes thousands of years to reach the surface as it slowly travels through layers of gas and plasma. The light that eventually emerges from the surface spreads out through space at incredible speed. It travels across the star's developing planetary system, warming the dust and gas of the disk, illuminating the newly formed planets and moons, and casting shadows across their surfaces. Some of this light continues outward for years or centuries, crossing the vast emptiness between stars. Much of it will never be intercepted by anything at all. It will journey through interstellar space, a silent message born from the star's internal fire. As you move closer to the star, imagine descending toward its surface. You cannot land on it, of course, for stars have no solid ground, but you can drift close enough to feel the intense energy rising upward. The surface, known as the photosphere, is a seething ocean of plasma. Bright granules form and dissolve in patterns that look like slowly shifting speckles. Each granule is a cell of rising hot gas, glowing brightly before it cools and sinks back into the star's interior. This cycle continues endlessly, creating a textured, living landscape of light and motion. Occasionally, magnetic fields twist and rise through the surface, creating dark areas called sunspots. These spots are cooler than their surroundings, though still hotter than anything on a planetary surface. From these active regions, loops of charged particles arc outward into space, forming towering structures known as prominences. When these magnetic fields snap and realign, they produce flares, sudden bursts of energy that shoot outward into space. Yet even these flares, though powerful, do not disrupt the star's overall stability. Its light remains steady, like a calm beacon glowing through the cosmos. Every star on the main sequence has its own personality. Smaller stars, known as red dwarfs, burn slowly and dimly, conserving their hydrogen with remarkable thrift. They can live for trillions of years, far longer than the current age of the universe. Their light is gentle, a soft reddish glow that warms their surroundings with quiet endurance. Larger stars, on the other hand, burn hot and bright. Blue and white stars produce tremendous amounts of energy, but they consume their fuel quickly. They live fast, shining fiercely for millions rather than billions of years. The star you observe may fall somewhere in between, neither too small nor too massive, glowing with a warmth that supports long-term stability. As the star continues to shine, its light shapes everything nearby. If planets have formed around it, they begin to settle into their orbits. The closest planets feel intense heat, their surfaces warm and bright. Further out, colder worlds form, their atmospheres thin and frigid. Beyond these planets, comets and icy objects drift at the edges of the star's domain, occasionally disturbed by gravitational nudges that send them inward toward the warmth. All of these objects orbit in a steady rhythm, held in place by the star's gravitational embrace. Now, Drift outward, away from the star and its planets, until you reach the thin boundary where the star's wind fades into the interstellar medium. Here, particles released from the star, tiny fragments of plasma, continue their outward journey until they merge with the gas between stars. The star's presence is felt even at this great distance. Its magnetic field stretches far into space. Its light, though faint from afar, contributes to the gentle illumination of cosmic dust clouds. The star has become part of the tapestry of its galaxy, one of hundreds of billions of stars woven into a swirling cosmic structure. If you rise even farther, imagining yourself floating above the galactic plane, you can see how stars collectively shape the galaxy. Their combined light forms the luminous band of the Milky Way. Gas clouds glow with reflected starlight. Dust lanes darken some regions, hiding newborn stars within. Star clusters shimmer like jewels suspended in the cosmic sea. The galaxy is alive with motion, rotating slowly around its center, its spiral arms stretching outward like cosmic rivers of light. Your star, like all main sequence stars, contributes to this grand design. Its light travels across the galaxy, mingling with the light of countless others. Its gravity helps hold nearby objects in place. Its radiation influences the chemistry of surrounding gas. The star is a single point of brilliance, yet it participates in the collective glow of the entire galaxy. Its stability allows for the possibility of life to emerge on any planets it warms. Its constancy provides the rhythms that shape planetary climates, tides, and seasons. Life, if it begins near such a star, will do so quietly. The star's warmth creates the conditions for water to remain liquid on suitable planets. Its steady glow ensures that temperatures do not fluctuate wildly. Atoms forged in ancient stars, carbon, oxygen, nitrogen, and more, combine in new ways on the surfaces of young worlds. Molecules form, break apart, and form again. Energy from starlight drives chemical reactions that may one day give rise to living cells. The star itself is unaware of this, of course. It simply shines, offering light and warmth as byproducts of the fusion in its core. Yet its light makes life possible, guiding the growth of plants, driving the cycles of oceans, and shaping the destinies of any beings that may one day gaze upward and wonder about the stars. You drift closer again to the star, watching the endless processes of fusion and convection unfold. Hydrogen atoms are consumed at an astonishing rate, thousands of kilograms every second. Yet because stars are so massive, this fuel lasts for billions of years. The star's core gradually fills with helium, the byproduct of fusion. Over time, the core temperature rises slightly as it becomes denser. The star's brightness increases slowly, so gradually that no living creature would notice during its lifetime. The star is changing, but the change is gentle, unfolding across vast scales of time. Under the surface, deep currents of plasma flow outward from the core, carrying energy to the outer layers. These currents create a complex network of magnetic forces that twist and snap like invisible threads. Occasionally, these magnetic forces align in ways that funnel charged particles into streams that arc outward into space. These streams form patterns, shaping the star's corona, a halo of superheated plasma surrounding the star. The corona's temperature is far hotter than the surface, reaching millions of degrees. The reason for this heat remains one of astrophysics' great mysteries. Yet the corona's presence adds to the star's radiation, bathing the surrounding space in a gentle glow of X-rays and ultraviolet light. The star's light defines time itself for any worlds that orbit it. Days, seasons, and years are all measured by the rising and setting of its glow. Its gravitational pull defines the rhythm of orbits. Its stability allows complex systems to form. Imagine drifting above a planet warmed by this star. Snow gleams faintly in winter, melting as the star's light returns in spring. Lakes shimmer, winds blow softly across plains. Life adapts to cycles shaped entirely by the star's glow. Over millions of years, the star continues to shine with unwavering brilliance. Light from its surface travels outward into space, carrying with it the story of its internal processes. This light will illuminate gas clouds, reflect off dust grains, and be absorbed by the atmospheres of distant worlds. Some of the photons leaving the star right now will not reach their destinations for thousands of years. Others will wander through space indefinitely. Each photon carries energy that originated in the star's core, from a fusion reaction that occurred long before the light reached the surface. As the star ages, the hydrogen in its core gradually diminishes. The star compensates by contracting slightly, raising the core temperature and increasing the rate of fusion. The star becomes brighter, though the change is so subtle that it spans millions of years. Stars live in timeframes so vast that entire civilizations could rise and fall without observing any significant change. Imagine drifting through the star's planetary system during this long and stable period. Worlds orbit with predictable motions. Asteroids collide occasionally, creating fragments that drift through space. Comets in distant orbits swing inward when disturbed, their icy tails glowing faintly in the star's light. The star watches over all of this with steady brilliance, its presence a constant in an ever-changing system. Stars on the main sequence are like candles in the darkness of the universe. They burn calmly, steadily, and beautifully. Their lives are long and luminous. They illuminate galaxies, enrich their surroundings with energy, and create environments where matter can assemble into worlds. The star before you is one such candle, glowing with warmth and stability. You drift closer once more, feeling the gentle pressure of its radiance. The star is in the prime of its life, shining with a sense of purpose. It will remain in this state for billions of years. It will continue to fuse hydrogen into helium with unwavering efficiency. It will remain a beacon in the cosmic night, filling space with its golden glow. As you watch this steady brilliance, you begin to sense that the star's life, though long and peaceful, is part of a larger cycle. It was born from darkness. It now shines brightly, and one day, far in the future, it will change again. Its hydrogen will eventually be consumed. The balance between gravity and pressure will shift. The star will enter a new phase of existence, one filled with expansion, transformation, and profound beauty. For now, however, it shines. It breathes light into the universe. It warms the worlds around it. It shapes the environment with its gravity, and it illuminates the path ahead in this cosmic journey. The life of light is long, steady, and filled with quiet elegance. It is the heart of what stars are. And as you drift in the glow of this radiant sphere, you prepare to enter the next chapter of its journey, where the star will reveal a deeper purpose. The forging of elements, the creation of the building blocks of life, and the continuation of a cycle that spans the entire cosmos. Element makers. Within the warm and glowing heart of a mature star, something extraordinary unfolds, quietly, steadily, and with unfathomable power. Stars are not only sources of light, they are forges. They are the cosmic furnaces where the raw materials of the universe are transformed into the elements that make up everything we know. As you drift near the glowing surface of the star, imagine descending once again toward its inner layers, not to be consumed or overwhelmed, but to observe with calm, steady awareness the gentle yet profound processes unfolding within. Deep in the core, hydrogen continues to fuse into helium, releasing light and warmth. But as time passes, something else begins to accumulate: helium itself. The star's core gradually fills with this heavier element, forming a denser, hotter region that settles toward the center. For millions and billions of years, this process continues, building a reservoir of helium that will one day ignite into something completely new. This ignition, when it arrives, marks the beginning of a star's transformation from a simple source of light into a creator of atoms far more complex. You drift quietly through layers of plasma, watching the slow gathering of helium atoms in the core. The star continues to burn steadily on the main sequence, but its core temperature rises ever so slightly each million years. When enough helium accumulates, the conditions shift. The temperature and pressure increase until helium nuclei, which are more resistant to fusion than hydrogen, begin to collide with enough force to merge. This process is known as the triple alpha reaction. It is a delicate dance of energy and probability, requiring immense conditions that only stars can provide. Imagine the moment helium fusion begins. It is not sudden or explosive, but it is powerful. Helium atoms fuse to form carbon, one of the most essential elements in the universe. Carbon is the backbone of life. It forms the framework of complex molecules. It is the atom that allows chains, rings, and intricate structures to emerge. The star, without knowing it, without intention, is creating the element that will someday give rise to forests, oceans, living creatures, and the cells that make up your own body. As carbon accumulates, some of it fuses again, eventually forming oxygen. The temperature rises further. New reactions become possible. Neon, magnesium, sodium, and aluminum appear, forged through the immense pressures at the star's center. These elements spread outward in slow currents, mixing gently into the star's outer layers. But the creation of these elements is only the beginning. In stars far more massive than the one you observe, the process continues to even greater depths. Their cores become hot enough to fuse carbon into heavier elements like neon and oxygen. Later, these massive stars produce silicon, sulfur, and ultimately iron. Iron forms the boundary of energy production, the point at which fusion no longer releases energy but requires it. To fuse iron drains a star rather than fuels it. So iron becomes the last element a star can create through ordinary fusion. Yet the universe contains elements far heavier than iron: gold, uranium, platinum, and more. These elements are produced through processes that require even more extreme conditions. Conditions that occur only at the violent deaths of massive stars. But the seeds of those elements begin here, in the quiet build-up of matter within stars during their lifetimes. As you drift inside this glowing furnace, imagine the cycles of fusion unfolding like slow, rhythmic breaths. The star breathes hydrogen in and helium out. It breathes helium in and carbon out. It breathes carbon in and oxygen out. Each stage requires more heat, more pressure, and more time. These cycles turn the interior of the star into layered shells, like the rings of a tree, each layer fusing different elements as the star ages. The outer layers remain cool and calm, even as the core grows increasingly complex. The star's role as an element maker is essential for the universe itself. Without stars, the universe would consist almost entirely of hydrogen and helium, simple gases that lack the complexity to form planets, oceans, mountains, or living beings. Stars transform simplicity into richness. They take basic ingredients and, under the pressure of their massive hearts, create the diversity needed for galaxies to grow into places of complexity. Imagine drifting through a cloud of gas, enriched by the winds of older stars. These winds carry carbon, oxygen, nitrogen, and other elements into space. Over time, this enriched gas becomes the material for new stars and planets. Your own world, your own body, your own breath, all contain atoms forged billions of years ago inside stars that lived and died long before the sun was born. Carbon in your cells, oxygen in your lungs, calcium in your bones, iron in your blood. Every atom heavier than hydrogen was created by stars. This connection is not poetic metaphor. It is literal. You are made from stardust, shaped by processes that unfolded in stellar cores and explosive endings. The universe recycled those atoms countless times before they became part of you. As you drift through the star's outer layers again, imagine the light emerging into space, carrying with it information about the elements being made inside. Astronomers can analyze this light, breaking it into spectra that reveal the chemical fingerprints of the star. Every element absorbs and emits light in unique patterns. These patterns allow us to understand the star's composition without ever touching it. The star's light becomes a message, carrying knowledge across space. The life of a star is a symphony of creation, a slow and steady orchestration of fusion reactions that build the elements of the cosmos. But stars cannot fuse elements forever. They consume their fuel, and in time, even the most powerful ones must face the limits of their energy. The star you observe will one day exhaust the hydrogen in its core, then the helium, and slowly move through its stages of evolution. The elements it creates will become its legacy, released into space through the winds, nebulae, or explosive ends. For now, the star continues its quiet work. Fusion hums steadily at its center, atoms merging in gentle waves of light and heat. The star shines not only with brightness, but with purpose. It is shaping the universe around it, enriching it with the elements of future worlds. Drift near its surface and feel the warmth, a warmth that carries the memory of ancient stars and the promise of future creation. As you move outward, imagine looking back at the star glowing softly against the backdrop of space. Its light is calm, its energy steady, its core quietly building the elements of existence. The star does not know the significance of what it creates, yet it is the universe's great alchemist. Its fusion furnaces turn fire into matter, turning energy into structure, turning simplicity into the rich complexity that makes galaxies vibrant and worlds possible. You drift past the star's luminous surface once more, preparing to witness how the incredible variety of stars in the universe leads to diverse lifetimes, sizes, temperatures, and destinies. For every star, the path of evolution depends on one crucial factor: mass. And it is here, in the next chapter, that the universe reveals the vast library of stellar types, from tiny red dwarfs to immense blue giants, each living a different story written in the language of light. Giants and dwarfs. Across the vast expanse of the universe, stars reveal a breathtaking diversity of sizes, colors, temperatures, and lifetimes. Though their lives all begin in the quiet collapse of a nebula, the path they follow after birth depends almost entirely on one thing: their mass. Mass determines a star's brightness, its temperature, its lifetime, its internal fusion processes, and ultimately, its fate. As you drift among the stars, imagine them scattered like glowing embers across an infinite cosmic canvas. Each ember is a different story, a different rhythm of light and heat, shaped by the weight of the gas cloud from which it was born. Start with the smallest stars, the tiny red dwarfs. These stars are gentle, modest in size, and incredibly long-lived. A red dwarf may be only a tenth the mass of the Sun, or even smaller, glowing with a soft reddish hue that seems closer to embers than flames. They burn their hydrogen fuel with extreme efficiency, consuming it so slowly that their lifespans stretch into the trillions of years. The universe itself is not yet old enough to have seen a single red dwarf die, for even the smallest and faintest among them live longer than the cosmos has existed. Imagine drifting near one of these quiet stars. Its light is subtle, warm, and faint. The surface temperature is lower than the Sun's, giving it a reddish glow. The star feels calm, almost shy in its radiance. It shines not with brilliance, but with persistence. Red dwarfs burn their fuel so slowly and evenly that they never undergo dramatic expansions or violent deaths. Instead, they change gradually over immense stretches of time, growing slightly dimmer as they age, and eventually fading into darkness trillions of years from now. Around such stars, planets may form in tightly bound orbits, warmed by a steady but gentle glow. Now drift towards stars similar in mass to the Sun, medium-sized stars that strike a balance between longevity and brilliance. These stars glow with a comforting golden white light. They live for billions of years, stable and calm during their long main sequence phases. Their surfaces simmer gently with convection, their cores steadily fuse hydrogen, and their surrounding systems evolve in quiet, predictable cycles. Stars like these are the ones most likely to host planetary systems with stable climates and conditions suitable for life. The Sun, in its calm middle age, is such a star. A star like the Sun spends the majority of its life in peaceful equilibrium. It is neither too large to burn violently, nor too small to be faint. It lives for billions of years, shining steadily, warming planets, creating environments where chemistry can flourish, and potentially giving rise to life. You drift near such a star and feel its warmth radiating evenly outward. Its gravity holds its planetary system together. Its light shapes climates, and its presence defines the rhythms of days and seasons for any worlds that orbit it. Now, drift farther into space, towards stars of greater mass. These are the blue and white giants, enormous and blazing with intensity. Their surfaces reach temperatures tens of thousands of degrees hotter than those of smaller stars. They shine fiercely, casting brilliant blue-white light into the darkness. Their fusion is rapid and voracious. They consume their hydrogen fuel at astonishing rates, burning through resources in millions rather than billions of years. These stars are massive, powerful, and short-lived. Their brilliance is breathtaking, but it comes at a tremendous cost. Imagine drifting near one of these massive giants. Its light is overwhelming, almost too bright to gaze upon directly. The star roars with energy, its surface boiling with intense pressure, its winds blowing outward with incredible force. The ultraviolet light it emits shapes its surroundings dramatically, ionizing the gas around it and creating stunning nebulae that glow in magnificent hues. These stars sculpt their environments, influencing star formation within their vicinity. They are the kings of stellar evolution, massive, intense, and destined for spectacular deaths. The most massive stars in the universe may be dozens or even hundreds of times the mass of the Sun. These extreme stars are rare, born only in the densest and richest star-forming regions. Their lives are brief, measured in a few million years. Yet, in that short time, they shape entire regions of their galaxies. They emit vast amounts of radiation. They produce heavy elements in their cores at a rapid pace. Their powerful winds blow bubbles in the interstellar medium, carving out enormous cavities that expand through the space like ripples from a stone dropped in water. Each star, whether giant or dwarf, lives according to the dictates of mass. Mass determines brightness, temperature, fuel consumption, and evolution. But in this diversity lies the beauty of the cosmos. Tiny red dwarfs provide quiet stability. Medium stars like the Sun offer long, steady light that allows for the development of worlds. Massive stars burn intensely, enriching the universe with heavy elements through their explosive deaths. Together, they create the balance that allows galaxies to grow, evolve, and recycle matter through countless generations of stars. As you drift through this stellar landscape, imagine the spectrum of colors that fill space. Red dwarfs glow with soft warmth. Orange and yellow stars sparkle with familiar radiance. White stars shine with clean brilliance. Blue giants blaze with blistering intensity. These colors reflect their temperatures and masses, turning the galaxy into a masterpiece of shifting light. No two stars are exactly alike. Each glows with its own signature of temperature and composition. Each tells a story written in the language of fusion and gravity. Consider the smallest of all stars, brown dwarfs, often called failed stars. They form like stars but lack the mass to ignite sustained hydrogen fusion. Brown dwarfs glow faintly in infrared, their surfaces warm but dim. They drift quietly through the galaxy, too cool to shine brightly. Though they lack the brilliance of true stars, they are important members of the cosmic family. Some host planetary systems of their own. They exist in silence, their faint glow offering a gentle reminder that not all objects in the universe achieve full starlight, yet each plays a role in the greater cosmic tapestry. Then there are the supergiants, stars so vast that if placed at the center of our solar system, they would engulf the orbit of Earth or even Mars. Their surfaces swell with pulsations. Their light is intense and unsteady. These stars live brief, dramatic lives, burning through their fuel with astonishing speed. Their cores undergo rapid fusion cycles, creating layers of different elements in shells, like cosmic onions. They are unstable, powerful, and destined for explosive ends. Yet their short lives enrich the universe with heavy elements, making worlds like ours possible. You drift among these stars, feeling the texture of their light, the rhythm of their lives, and the profound diversity that fills the galaxy. The quiet red dwarfs, the steady suns, the brilliant giants. Each star contributes something essential to the cosmos. Their differences create balance. Their variety shapes galaxies. Their lives set the stage for chemical evolution, planetary formation, and biological possibility. Stars are not solitary in their influence. Many form in pairs, known as binary systems. Two stars orbiting each other create complex gravitational dances. Their interactions can shape their evolution in surprising ways. Mass transfer between stars can rejuvenate old stars, alter fusion processes, or trigger nova events. In some binary systems, a white dwarf pulls matter from a companion star, creating powerful explosions that briefly shine brighter than an entire galaxy. Binary stars remind us that stellar life is not always lived in isolation. Some stars share their destinies closely with others. Even clusters of stars, born from the same cloud, display immense diversity. Some stars in the cluster will live for millions of years, while others will live for trillions. The cluster ages as a group, but individual stars evolve according to their mass, creating a wide range of outcomes from a shared beginning. You drift through one such cluster now, watching stars of all sizes glowing in tight proximity, forming a luminous swarm that drifts gracefully across space. As you observe the stars, you begin to sense a deeper truth. Although they differ greatly in mass, temperature, and brightness, they all follow the same fundamental pattern. Birth in a nebula, life powered by fusion, change fueled by the consumption of hydrogen, transformation into giants or dwarfs, and eventually, death. Some quiet, some explosive, but all part of a repeating cycle that enriches the universe. The fate of every star is written in its mass. And the next stage of this story, the transformation of stable stars into swelling giants, marks one of the most beautiful and poetic phases of their existence. For as stars age and exhaust their hydrogen fuel, they begin to change dramatically. Their outer layers expand, their surfaces cool, their colors shift. They become red giants, vast, luminous, and breathtaking. Now, as you drift among stars of many sizes and ages, you prepare to follow the sun-like star into its next great transformation. The quiet stability of the main sequence gives way to a new chapter. A chapter of expansion, cooling, and gentle shedding. A chapter where stars reveal their inner layers and create cosmic sculptures of glowing gas. A chapter known as the breath of the red giant, the red giant's breath. As a star like the sun ages, its long season of stability gradually comes to an end. For billions of years, it has balanced two opposing forces, gravity pulling inward and the pressure from fusion pushing outward. This balance has kept the star calm and luminous, shining steadily through the darkness. But eventually, the hydrogen fuel in its core becomes depleted. The helium ash that has accumulated there grows dense and heavy, and the balance begins to shift. This is the moment when the star prepares to breathe outwards, expanding into something vast and extraordinary. Imagine drifting near the star as this transformation begins. Deep inside the core, hydrogen fusion slows and is eventually exhausted. Without the energy of fusion to support it, the core begins to contract under its own weight. As it contracts, it heats up, becoming hotter and denser with every passing moment. Around this contracting helium core, however, there is still hydrogen remaining in a shell. The rising temperature ignites this shell, causing hydrogen to fuse into helium once more. This shell burning releases an enormous amount of energy, far more than the core's fusion did during the star's youth. The sudden increase in energy pushes outward with tremendous force. The outer layers of the star expand in response, swelling outward and cooling as they grow in size. The star's surface temperature drops, giving it a reddish tint. Over time, the star grows larger and brighter, transforming into a red giant. This name describes the two defining characteristics of this phase: its massive size and its deep, warm color. As the star expands, its radius grows to hundreds of times its original size. If a sun-like star were placed at the center of our solar system during its red giant phase, it would engulf the orbits of Mercury and Venus, and perhaps even draw near to Earth. The star that once seemed modest and steady now fills the sky with a crimson glow. From your vantage point drifting nearby, you can see the star's surface ballooning outward in slow, majestic waves. It does not grow smoothly. It pulses, expanding and contracting gently as its interior adjusts to the new balance of pressure and gravity. The surface of the red giant is cooler than before, only a few thousand degrees, but its size more than compensates. The star becomes far brighter overall, shining with a luminous intensity that bathes nearby space in a warm, reddish light. Massive convection currents churn within its outer layers, rising and falling like slow, massive tides of glowing plasma. These currents carry material from deep within the star up to the surface, bringing freshly produced elements with them. Carbon, nitrogen, and oxygen begin to appear in the outer layers, products of the internal fusion that took place earlier in the star's life. As the star expands, it also begins to lose mass. The outer layers are not tightly held by gravity anymore, and the star gently sheds material into space. Stellar winds carry gas and dust outward, forming delicate veils around the red giant. Imagine drifting through these winds, seeing them shimmer in the starlight like fine, swirling mist. The material being released into space will someday form new stars, new planets, and new systems. The star, now in its old age, is giving back to the galaxy. It is exhaling the elements it created, releasing them in soft, sweeping motions. This shedding of material accelerates as the star becomes more unstable. Pulsations grow stronger. The outer layers expand and contract with increasing intensity. Each pulse pushes more gas outward, forming concentric shells of material that drift away from the star. These shells create stunning nebulae, clouds of glowing gas that shine with the light of the aging star at their center. From your vantage point, you can see these nebulae forming in graceful, rippling arcs. They glow faintly with hues of red, blue, green, and violet, each color corresponding to specific elements illuminated by ultraviolet radiation from the star's inner layers. The red giant phase can last hundreds of millions of years, depending on the mass of the star. Throughout this time, the star breathes outward in gentle waves, each cycle carrying more of its outer layers into space. Inside the core, helium itself begins to heat to extraordinary temperatures. When the core reaches around 100 million degrees, helium fusion suddenly ignites in a process known as the helium flash. This event is brief and intense, occurring in only a few seconds, but its effects are profound. Helium nuclei fuse into carbon and oxygen, releasing an enormous amount of energy. Yet from the outside, you would see almost nothing. The helium flash happens deep inside the opaque layers of the star, and the energy is absorbed before it reaches the surface. What you observe instead is a subtle contraction of the star as the core stabilizes with new fusion. The red giant becomes slightly smaller and less luminous for a time, though still vastly larger than in its youth. With helium now burning in its core, the star enters a new stable phase. It glows warmly, radiating light from the fusion of helium into carbon and oxygen. This stage is shorter-lived than the long main sequence phase, lasting only a fraction of the star's lifetime. During this time, the star continues to shed its outer layers gently, enriching the space around it with elements that will one day become building blocks for new systems. Drift closer to the star's surface and observe the massive convective cells rising and falling, carrying material to the surface in slow, immense motions. These cells can be as large as the entire distance from the Sun to Earth. They churn with quiet power, transporting heat from the interior outward. The surface of the red giant appears mottled, glowing in patches that shift gradually, like a living, breathing canvas of light. As helium fusion continues, the core becomes richer in carbon and oxygen. Eventually, the helium is exhausted. The star then faces another inevitable shift. It cannot fuse carbon or oxygen without far more mass. So once again, fusion slows and the core begins to contract. The outer layers, becoming unstable and unbound, expand even further. The star enters a second red giant phase, even larger and more luminous than before. This stage marks the last great breath of the star's life as a giant. The outer layers become so distended that they drift away in steady waves. The star loses its mass more rapidly now, shedding enormous amounts of gas. This gas drifts outward, forming a shell around the star that glows in soft, ethereal colors. These glowing shells become planetary nebulae, delicate, symmetrical shapes sculpted by the star's winds and radiation. They appear as circles, ellipses, or intricate patterns that resemble the flowers, hourglasses, or swirling wings. The beauty of these nebulae comes from the interplay of radiation and gas, each layer illuminated by the star's final glow. From your vantage point, as you float beyond the star's surface, you can see this planetary nebula forming in real time. The gas expands outward in slow motion, forming translucent layers that ripple gently. The colors deepen as ultraviolet light ionizes the gas, making it shimmer like a cosmic aurora. And in the center, the star slowly contracts, becoming hotter even as it loses mass. As the outer layers drift away completely, what remains of the star is a small, brilliant core surrounded by a glowing nebula. This core shines intensely, radiating ultraviolet light that causes the gas around it to glow. Over time, the nebula expands further, becoming thinner and more diffuse until it eventually fades into space. The elements released by the star, carbon, oxygen, nitrogen, and more, mix with the interstellar medium. They will eventually become part of new stars, new planets, and perhaps new living beings. The transformation of a star into a red giant is one of the universe's most graceful processes. It is a slow, majestic expansion, like the unfolding of a cosmic flower. It is a process of release and renewal, where the star gives back the elements it created in its lifetime. The red giant breath is not a violent end. It is a gentle transition, a soft exhalation of light and matter that enriches the galaxy. As you drift through the expanding nebula, surrounded by glowing gas and shimmering dust, you feel a sense of calm. The star has completed its long journey through stability and has now entered its final, beautiful phase of transformation. The red giant breathes outwards, filling the surrounding space with a soft, colorful glow. And at the heart of this glowing shell lies the future of the star's evolution, awaiting the next chapter. For some stars, the red giant phase is the last major transformation before they shrink into quiet remnants. But for the most massive stars, the story is far more dramatic. These giants do not end with gentle nebulae. They continue to fuse heavier and heavier elements, building toward a final, catastrophic collapse that will reshape the cosmos on immense scales. The next part of the journey leads into the heart of this extraordinary event, where the universe unleashes one of its most powerful and spectacular forces, the supernova. Supernova. In the deep reaches of the galaxy, where massive stars burn with ferocious brilliance, a different kind of ending unfolds. Unlike stars that drift gently into their red giant phases and exhale their outer layers softly into space, the most massive stars meet their fate in immense and spectacular explosions. These events are rare, dramatic, and transformative, reshaping entire regions of the galaxy. They are known as supernovae, and they represent one of the universe's most powerful expressions of change. Imagine drifting near a massive star as it nears the end of its life. This star is much larger and hotter than stars like the Sun, shining with a fierce, bright blue light that fills space with intense radiation. For millions of years, it has dominated its surroundings, sculpting the gas around it with its powerful stellar winds, illuminating nearby nebulae and influencing star formation in its region. But now, something deep within the star is beginning to shift. The core of this massive star has moved far beyond the simple fusion of hydrogen into helium. Over its lifetime, it has fused helium into carbon, carbon into oxygen, oxygen into neon, neon into magnesium, magnesium into silicon, and eventually silicon into iron. Each fusion stage requires higher temperatures and shorter timescales. Carbon fusion may last 1,000 years. Oxygen fusion lasts only months. Silicon fusion lasts mere days. The star races through these final stages with a sense of urgency, burning hotter and faster as it attempts to sustain its energy output. But iron marks a boundary in the universe. When nuclei fuse into elements lighter than iron, energy is released. When heavier elements are made, energy is consumed. Iron cannot be fused to produce more energy. And so when the core fills with iron, the star reaches the end of its ability to support itself through fusion. The energy that has held gravity at bay begins to fade. Imagine drifting closer as the fusion in the core slows. The star's brilliant light remains steady from the outside, but its heart is collapsing in on itself. Without outward pressure from fusion, gravity takes control. The core contracts rapidly, heating to unimaginable temperatures in the process. The collapse accelerates, and within seconds the core's material is crushed into a state so dense that electrons and protons merge to form neutrons. The core becomes a neutron-rich ball of matter, something so dense that a teaspoon of it would weigh billions of tons. This sudden shift creates an incomprehensible shockwave. The core bounces slightly as it collapses into a neutron-dense sphere, sending ripples outward through the star's interior. Meanwhile, the outer layers of the star continue to fall inward, unaware that the core has reached its limit. When these layers strike the neutron core, they rebound violently. Neutrinos, tiny, nearly massless particles created in enormous numbers during the collapse, burst outward in a flood. Though they almost never interact with matter, the sheer number of neutrinos helps transfer energy to the outer layers of the star. Then, in a moment of unparalleled cosmic force, the star explodes. The supernova erupts with a brightness so intense that it can outshine an entire galaxy for days or weeks. Imagine being present near this explosion, observing from a safe, impossible distance as the star's outer layers are hurled into space at incredible speeds. The shockwave tears through the star's atmosphere, blasting away gas, dust, and stellar material with unimaginable energy. The eruption releases more energy in a few seconds than the Sun will release in its entire 10 billion year lifetime. From your vantage point in space, the explosion appears like a sudden and overwhelming flash of light. A brilliant sphere expands outward, glowing in fierce shades of white, blue, and violet. The supernova's flash illuminates nearby nebulae, casting long shadows across the dust and gas of the galaxy. The explosion sends waves of radiation in all directions: X-rays, gamma rays, ultraviolet light, and visible light, all racing outward at the speed of light. The shock wave continues to expand, sweeping through the interstellar medium like a tidal wave of energy. As the gas cools slightly, the explosion begins to display swirling colors: deep reds from hydrogen, emerald greens from oxygen, and blue-white glows from helium and other elements. The remnants of the star form a nebula of stunning complexity, filled with knots, filaments, and twisting patterns sculpted by the turbulence of the explosion. But the supernova is more than just a spectacular event. It is a forge of extraordinary power. In the heart of the explosion, the temperature rises so high and the pressure becomes so intense that elements heavier than iron are formed. Gold, platinum, uranium, and other rare elements are created in these fleeting moments. The explosion scatters these atoms across space, mixing them into the interstellar medium where they will eventually become part of new stars, planets, and living beings. Drift through the expanding cloud of the supernova remnant and imagine passing through regions rich with heavy elements. These atoms carry the signature of the star's last act, forged in the violent heart of the explosion. As the shock wave travels outward, it compresses the gas it encounters, triggering new waves of star formation. In this way, the death of one massive star leads to the birth of many others. The supernova becomes a catalyst for renewal, enriching the galaxy with elements and igniting the formation of future generations of stars. The remnants of the explosion expand for thousands of years, slowly cooling and spreading out across space. Some of the gas will blend into the galactic medium. Some will join new nebulae. Some will remain in beautiful and well-defined structures for millennia, glowing softly as they reflect the radiation from the core left behind. At the center of the expanding cloud, the fate of the star's core depends on its mass. If the core is between about 1 and 2 times the mass of the Sun, the collapse forms a neutron star, an object so dense and compact that it defies ordinary understanding. If the core is even more massive, gravity overwhelms all resistance, and the core collapses into a black hole, a region of space-time where gravity is so strong that nothing, not even light, can escape. For now, drift among the remnants of the supernova. The gas glows with vibrant colors. Shock waves ripple outward. Dust and heavy elements float through space, illuminated by the soft blue glow of radiation. It feels as though you are watching the universe create something new from the remains of something old. The beauty of this moment is overwhelming. The colors shift, swirl, and evolve over time, forming a tapestry of light that fills the cosmic night. From a distance, the supernova remnant becomes a glowing bubble embedded in the galaxy. Its expanding shell continues to shine for thousands or even tens of thousands of years. But its influence lasts far longer, as the elements it released become seeds for future creation. The iron in your blood, the calcium in your bones, and the gold in your jewelry were all born in events like this. billions of years before the sun existed. The universe recycles its stars, turning their deaths into the ingredients of future life. As you drift away from the glowing nebula, you feel a profound appreciation for the cycle that plays out across the galaxy. Massive stars live fast and die in brilliant explosions, but their deaths enrich the cosmos and set the stage for new beginnings. Supernovae are the universe's way of reshaping itself, redistributing matter, and ensuring the continuation of cosmic evolution. The story of a star does not end with the explosion. The core left behind carries its own mysteries, its own structure, and its own unique beauty. For some stars, that remnant becomes a neutron star, one of the densest and most extraordinary forms of matter in the universe. For others, the core collapses into a black hole, a silent and powerful object that bends space and time around it. Now, as you leave the brilliant debris of the supernova behind, the journey continues deeper into the aftermath of stellar death. Ahead lies the strange and captivating world of neutron stars, remnants so dense, so extreme, and so mesmerizing that they challenge the limits of our understanding. Neutron stars. In the quiet aftermath of a supernova, long after the blinding flash has faded and the swirling debris has begun to drift outward, something astonishing remains at the center. It is not a star in the traditional sense. It no longer shines with the steady glow of fusion. It no longer burns hydrogen or radiates with the gentle warmth of a main sequence life. Instead, what remains is an object so dense, so compact, and so extreme that it challenges the limits of our understanding. This remnant is a neutron star. Imagine drifting toward the heart of the supernova remnant, past the glowing filaments of oxygen and sulfur, past the shock waves rippling through interstellar space, past the expanding clouds of dust enriched with heavy elements. As you move into the center, the light dims and the colors fade. The brilliant fury of the explosion has passed. In the middle of this quiet clearing sits the neutron core, still hot, still glowing faintly in high-energy radiation, but small, astonishingly small. A neutron star is only about 10 to 15 miles across. You could drive across it in less than an hour if it were somehow possible to stand on its surface. And yet, this tiny sphere contains more mass than our sun. The density is unimaginable. A single teaspoon of neutron star matter would weigh billions of tons on Earth. You drift closer, feeling the strange gravity tug at you, a pull so intense that space itself seems to bend and warp. The neutron star, despite its modest size, controls its surroundings with overwhelming force. The surface is smooth, but not solid in the way we experience solids. It is a crust, a lattice of tightly packed neutrons fused into exotic forms of matter. Beneath the surface lies a sea of neutrons, so densely packed that they behave like a quantum fluid. There are no atoms here in the ordinary sense. Electrons and protons have merged. Pressure has squeezed matter to the brink of physical possibility. The neutron star is a place where the rules of physics feel stretched, where matter exists in states unseen anywhere else in the universe. Drift closer still, and you notice something extraordinary. The neutron star is spinning. Most neutron stars rotate rapidly, some dozens of times per second, others hundreds of times. The collapse that formed the neutron star conserved the angular momentum of the massive star that preceded it, causing the core to spin faster as it shrank. This rotation is so fast, so smooth, that the neutron star becomes a cosmic gyroscope of perfect precision. If you could listen to the rhythm of its spin, it would sound like a steady, unwavering pulse. Some neutron stars have strong magnetic fields, trillions of times stronger than Earth's. These magnetic fields trap charged particles and accelerate them to near the speed of light. As the neutron star rotates, beams of electromagnetic radiation sweep across space, like the beams from a cosmic lighthouse. When these beams cross Earth, we observe them as pulses of radio waves, X-rays, or gamma rays. These neutron stars are known as pulsars. Imagine drifting far enough away to see the beams sweeping through space. They flash rhythmically, creating a steady flicker that echoes across the cosmos. The precision is breathtaking, so precise that pulsars have been compared to cosmic clocks. Their rhythm does not drift. Their timing is so reliable that astrophysicists use them to measure the expansion of space, detect gravitational waves, and map the structure of the galaxy. The light from these beams carries information about the neutron star's rotation, magnetic field, and internal structure. Each pulse is a message from an object so dense and so extreme that it stands on the boundary between matter and collapse. As the neutron star spins, its crust may crack under the strain, releasing bursts of energy known as starquakes. These starquakes create sudden changes in the rotation rate, like a tiny hiccup in the star's cosmic heartbeat. Drift closer again, to the very surface of the neutron star. If you could hover above it for a moment, you would witness a landscape absolutely unlike anything on Earth. Gravity is so strong that any irregularity on the surface, a mountain, a bump, can rise no higher than a few inches before being crushed flat. These tiny hills are called neutron star mountains, though the name barely conveys their scale. The surface glows faintly with heat left over from the collapse. Over time, neutron stars cool, radiating their energy into space in the form of X-rays. Some neutron stars are born in isolation, floating quietly in space after their supernova. Others remain in binary systems, orbiting a companion star. When a neutron star orbits close enough to another star, it can pull material from its companion. This matter forms an accretion disk around the neutron star, heating up as it spirals inward. The infalling gas crashes into the star's surface with unimaginable force, releasing bursts of X-rays in periodic flashes. These objects are known as X-ray binaries, and they are among the most luminous sources of high-energy radiation in the galaxy. Even more extreme are magnetars, neutron stars with magnetic fields so intense that they can tear atoms apart. Their magnetic fields are the strongest known in the universe. These fields can twist and snap, releasing bursts of gamma rays that travel across vast distances. Magnetars are rare, but their eruptions are powerful enough to be detected from halfway across the galaxy. Imagine standing near a magnetar. Space itself trembles under the influence of its magnetic field. The air around it, if air could exist there, would shimmer with energy. You drift cautiously, sensing its immense presence. As neutron stars continue their lives, they gradually slow down. Their rotation slows as they lose energy through radiation. Their magnetic fields weaken. Their pulses become less frequent. Eventually, they fade into the dark, becoming cold, quiet husks of matter. But even in this silence, their structure remains, a monument to the immense forces that shape them. Neutron stars are reminders of the universe's extremes. They are the bridge between ordinary matter and the abyss of gravity itself. They show us what happens when atoms are pushed beyond breaking, when matter is crushed to its most compact form without collapsing into a black hole. And they illuminate the night sky with rhythmic signals that travel vast distances, far beyond the reach of ordinary starlight. Drift slowly outward now, leaving the neutron star behind. Its pulses grow dimmer as you move away. The flicker of its beams becomes a distant heartbeat lost in the cosmic background. Ahead of you lies the possibility of an even stranger object. For not all massive stars leave neutron stars behind. Some are even heavier, even larger, even more extreme. And for these stars, the collapse does not stop with neutrons. Gravity overwhelms all resistance. The matter collapses into a point of infinite density, and a new kind of object forms, a black hole. Beyond the quiet pulse of the neutron star, the next chapter begins in the deep silence of curved space-time, where even light cannot escape. Black holes. Beyond the quiet, rhythmic pulse of a neutron star lies a region of the universe where matter collapses past every known limit, where space and time curve so sharply that even light cannot escape. These places are not simply objects in the traditional sense. They are phenomena, gravitational wells carved into the fabric of space-time itself. They are black holes. Imagine drifting through the remnants of the Supernova Nebula, leaving behind the glowing filaments of expanding gas, moving deeper into the quiet and empty space beyond. The light of the explosion fades, the colors soften, the dust thins. Ahead of you is a region where the collapse of the star's core did not stop at the formation of a neutron star. Instead, gravity continued to intensify. The pressure soared past any ability of matter to resist. Electrons merged with protons. Neutrons collapsed. Even quarks, the fundamental particles inside neutrons, could not withstand the compression. Everything fell inward, giving way to a gravitational pull so strong, so absolute, that it turned the core into something beyond ordinary physics. This is the birth of a black hole. Picture the core of the massive star shrinking, 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 collapsing past the threshold of stability into a singularity, a point of infinite density contained within a boundary known as the event horizon. The singularity is where all the mass of the core is compressed into an infinitely small point. The event horizon is the invisible sphere around it, the boundary beyond which nothing, not even light, can escape. You cannot see the singularity. You cannot see the event horizon, but you can feel the gravity. Drift closer now, slowly and calmly, sensing the pull grow stronger as you approach. The black hole itself does not emit light. It does not shine. Yet the space around it can glow brightly. Matter falling toward the event horizon forms an accretion disk, a swirling, spiraling ring of gas and dust, heated to extreme temperatures by friction and gravitational energy. The disk glows with brilliant X-rays and high-energy radiation. It forms a luminous halo around the black hole, a cosmic whirlpool that lights up the darkness. Imagine watching this disk from a safe vantage point. The gas moves at extraordinary speeds, orbiting the black hole in tight spirals. The closer it gets, the faster it moves, until it reaches the innermost stable orbit. Beyond that orbit, the gas plunges inward, disappearing from the universe once it crosses the event horizon. The light emitted by the accretion disk bends around the black hole, distorted by the intense curvature of space-time. You see a ring of warped light, a bright circular glow known as the photon ring. It forms because light itself can orbit the black hole before escaping. This shimmering ring marks one of the most fascinating phenomena in the cosmos, the shadow of the black hole. Black holes warp space and time. If you imagine a grid stretching across space, the black hole pulls it downward into a deep well, a curve so steep that nothing can climb up. Time passes differently near the event horizon. A clock that approaches the black hole would tick more and more slowly compared to a clock far away. From your vantage point, you might watch an object falling toward the event horizon appear to slow down, its light stretching into redder wavelengths, its motion becoming more languid. It would seem to freeze at the boundary, never quite crossing from your point of view. But to the object itself, the fall would continue seamlessly, slipping beyond the event horizon and into the unknown interior. The inside of a black hole is a place we cannot observe, cannot measure, cannot directly understand. Our laws of physics describe everything outside the event horizon with remarkable clarity. But inside, at the singularity, the equations break down. Gravity becomes infinite. Density becomes infinite. Space and time lose their meaning. We do not know what happens there. It is one of the deepest mysteries of the universe. Some black holes spin. In fact, many do. When a massive star collapses, any rotation it had is conserved, causing the black hole to spin rapidly. Spinning black holes create even more complex distortions of space-time. They drag space itself around with them, a phenomenon called frame dragging. If you drift near such a black hole, you would feel space twisting, pulling you sideways in addition to downward. Matter falling into a spinning black hole forms a disk that rotates in the direction of the spin, creating jets of high-energy particles that shoot out along the black hole's poles. These jets can stretch for thousands of light years, glowing brightly as they travel through interstellar or intergalactic space. Imagine watching one of these jets, narrow, bright, and unbelievably powerful, streaming from the poles of a spinning black hole. The particles inside travel near the speed of light. They pierce through gas clouds, illuminating them in long, glowing tendrils. These jets can shape entire galaxies, creating shock waves that trigger new generations of star formation. They are among the most energetic phenomena in the universe. Black holes come in many sizes. Some are only a few times the mass of the Sun, formed from the collapse of massive stars. Others are millions or billions of times more massive, lurking in the centers of galaxies. Every large galaxy, including the Milky Way, contains a supermassive black hole at its center. These giants control the motion of stars, shaping the structure of galaxies over billions of years. Imagine drifting toward the heart of the Milky Way. Thousands of stars crowd into the central region, swirling in complex orbits. At the very center is Sagittarius A*, the supermassive black hole that anchors our galaxy. It is about 4 million times the mass of the Sun. If you could hover safely near it, you would see stars whipping around it at incredible speeds. These stars move in tight, fast arcs, their orbits revealing the presence of the immense gravitational force at the center. Supermassive black holes form not from single stars, but from the merging of smaller black holes, from the collapse of enormous gas clouds, and from the gradual accumulation of matter over cosmic time. They grow slowly, feeding on stars, gas, and dust. When lots of material falls in at once, the black hole becomes active, forming a brilliant quasar, a beacon visible across billions of light years. The light from a quasar can outshine an entire galaxy, even though it originates from a region smaller than our solar system. Black holes are not eternal in their exact form. Over extremely long timescales, they slowly evaporate through a process called Hawking radiation. This radiation is incredibly faint, taking trillions of years to have any noticeable effect on large black holes. But in theory, even the most massive black hole will eventually evaporate, releasing its energy back into space. When the last star has faded and the universe has grown cold and dark, black holes will be among the final objects to remain. Their slow evaporation represents the final whisper of energy returned to the cosmos. As you drift near the event horizon of a calm, isolated black hole, you feel a deep silence. There is no sound here, no turbulence of surface or storm. There is only gravity, clean and unbroken. The black hole is perfectly smooth, perfectly dark, perfectly serene. It is not a monster. It is not a devouring creature. It is simply a region where gravity has become absolute, where the rules of the universe reach their most profound extreme. You drift backward now, watching the black hole recede into the darkness. Its shadow glows faintly with the distorted light of surrounding stars. The accretion disk flickers. The jet, if present, stretches upward into space like a beam of raw energy. The black hole stands as a reminder of the universe's power, its mystery, and its profound beauty. But black holes are not the only remnants of stars. Not every star is massive enough to collapse so completely. Many stars, including those like the Sun, end their lives far more gently. After shedding their outer layers and glowing briefly as planetary nebulae, they leave behind small, dense, gradually cooling cores known as white dwarfs. Now, as you drift away from the intense gravity of the black hole, the next chapter begins in the quiet, fading glow of these ancient stellar embers. White dwarfs. When a star like the Sun reaches the end of its long and luminous life, its transformation unfolds in gentle stages rather than violent collapse. It swells into a red giant, sheds its glowing layers into space, and reveals at its core a small, bright remnant. This remnant is not a neutron star, nor a black hole, but something far more peaceful, something soft in brightness, yet dense in form. Something that glows quietly for billions of years before gradually fading into darkness. This is a white dwarf. Imagine drifting closer to one of these ancient stellar embers. It sits at the center of a delicate planetary nebula, the luminous shells of gas it expelled during its red giant phase. The nebula glows with soft hues, pinks, blues, greens, colors shaped by the elements the star once forged. Over thousands of years, this nebula expands outward, becoming thinner and more diffuse until it blends into the interstellar medium. But the white dwarf at its center remains, shining like a tiny crystal suspended in space. From afar, the white dwarf looks like a faint, steady point of light, smaller than a planet, yet shining with the brilliance of a star. Move closer, and you see its surface glowing with a blue-white intensity. A white dwarf is incredibly dense, so dense that a fragment the size of a pebble would weigh tons on Earth. Its radius is similar to Earth's, yet its mass can rival that of the Sun. This density creates a gravitational pull so strong that, if you could approach the star's surface, a single step would be impossible. Gravity would pull you down with crushing force. Despite this intense gravity, white dwarfs are stable. They do not collapse further because of a quantum mechanical effect known as electron degeneracy pressure. This pressure arises from the fact that electrons refuse to be squeezed into the same state. It is a rule of nature that keeps the white dwarf from collapsing, even though fusion has ended and no new energy is being produced. The star has reached equilibrium in a new, unusual way, supported not by heat and pressure from fusion, but by the very structure of matter itself. Drift gently above the glowing surface. The white dwarf's atmosphere is thin and transparent, composed mostly of hydrogen or helium. Beneath this thin layer lies a dense crystalline core, rich in carbon and oxygen, elements forged in the star's earlier life. Over billions of years, this core slowly cools and begins to crystallize. Imagine the entire star gradually turning into a diamond-like structure, a crystallized sphere of carbon the size of Earth. This is not a poetic exaggeration. Astronomers believe many white dwarfs slowly become crystalline stars as they age. The surface of the white dwarf is smooth and unblemished, glowing with stored thermal energy. It does not flicker or pulse like a neutron star. It does not spin with extreme speed or emit powerful jets. Instead, the white dwarf cools gradually and silently, radiating away its heat over billions of years. It will never fuse elements again. It will never swell or collapse dramatically. It has entered a long and peaceful twilight. Imagine drifting farther out, viewing the white dwarf within the thinning remains of its planetary nebula. Over time, the nebula expands so far that its glow fades. The gas disperses into the galaxy. What remains is just the white dwarf, now exposed to the vast darkness of space, shining like a lone ember cooling on the hearth of the universe. Its light is steady and soft. It is the memory of the star's long journey. White dwarfs come in many varieties. Some are composed mostly of helium, formed from stars that never reached the temperatures needed for helium fusion. Others, like the Sun will someday produce, consist of carbon and oxygen. The most massive white dwarfs, those born from stars just shy of the threshold needed to form neutron stars, contain oxygen, neon, and magnesium. Regardless of their composition, these remnants all share the same quiet fate, a slow and steady cooling into darkness. Some white dwarfs exist alone, drifting quietly through interstellar space. Others remain in binary systems, orbiting close to a companion star. In those systems, the white dwarf's strong gravity can pull material from its companion. This matter spirals toward the white dwarf, forming an accretion disk that heats up and glows brilliantly. When enough material builds up on the white dwarf's surface, a sudden burst of fusion can occur. This event, known as a nova, briefly brightens the system, causing the star to flare in brilliance before settling back to its quiet glow. Novae can repeat, occurring again and again as material accumulates. In more extreme cases, if a white dwarf accumulates too much mass from a companion star and exceeds a critical limit known as the Chandrasekhar limit, it can undergo a catastrophic collapse. This collapse ignites a thermonuclear runaway, a Type Ia supernova. Unlike the massive star supernova you observed earlier, these explosions do not produce neutron stars or black holes. Instead, the white dwarf is completely obliterated, leaving behind only expanding, glowing gas and dust. The explosion is so bright and consistent that astronomers use it to measure distances across the universe. Type Ia supernovae have played a crucial role in discovering the accelerating expansion of the cosmos. But the white dwarf you drift beside now is quiet and stable, with no companion to disturb its slow cooling. It will continue to fade for billions upon billions of years. Eventually, After a time so long that the universe itself will have transformed beyond recognition, the white dwarf will cool until it stops shining altogether. At this final stage, the white dwarf becomes what is known as a black dwarf, a cold, dark, inactive remnant containing carbon and oxygen, cooled to near absolute zero. No black dwarfs exist yet, because the universe is far too young. It will take trillions of years for any white dwarf to cool so completely. As you drift around this peaceful stellar remnant, the sense of cosmic time becomes vast and tranquil. The white dwarf represents endurance. It is the lingering memory of light after a long and vibrant life. The nebula around it slowly dissolves, fading like exhaled breath into the surrounding galaxy. The elements it released, carbon, oxygen, nitrogen, mix with interstellar clouds, becoming part of the raw material for future stars and planets. You move farther from the white dwarf, watching it shrink into a tiny glowing point. Its light is steady, gentle, and calm. It will continue glowing long after the stars around it have gone through their own cycles of life and death. In this phase of its existence, the star is a quiet witness to the unfolding story of the galaxy. But the galaxy does not remain still. Even as old stars fade, new stars are forming. The dust and gas released by red giants, supernovae, and planetary nebulae gather in vast clouds. Gravity pulls them together. Dark nebulae form, and within those nebulae, the cycle begins again. Ahead lies a vast cloud of gas and dust, the birthplace of new stars. The next chapter leads into the quiet regions where starlight has not yet ignited, where the universe returns to darkness to begin anew. Here, the ashes of old stars give rise to the next generation in places known as star nurseries. Star nurseries. Deep within the spiral arms of galaxies, far from the bright clusters of mature stars, lie regions where darkness gathers. These are not empty voids, but dense, rich clouds of gas and dust, cosmic wombs that cradle the beginnings of new light. They are known as star nurseries, and within them, the universe renews itself in quiet, gentle cycles. Imagine drifting toward one of these vast molecular clouds, a place where the scattered elements left behind by dying stars come together to form something new. From a distance, the cloud looks like a dark patch against the bright glow of the Milky Way. Its thick dust blocks starlight, creating silhouettes that stretch across the sky like vast, shadowed shapes. But as you move closer, the darkness becomes textured. You begin to see fine dust grains drifting like smoke, filaments twisting through the cloud, and cool pockets of gas arranged in intricate patterns. This is a cold and silent realm, illuminated only by the faintest glimmers of starlight leaking from surrounding regions. The temperature here is just a few degrees above absolute zero. Molecules move sluggishly, drifting through the stillness. Inside these cold depths, gravity begins its quiet work. It pulls gas into denser regions, forming structures known as clumps and cores. These are the seeds of future stars. The cloud is unimaginably vast, spanning dozens or hundreds of light years. Within it, thousands of stars may be forming at once. Each core is like a tiny sanctuary, isolated within the greater darkness. Imagine drifting through these regions, moving silently past pockets of gas where the earliest stages of star formation are taking place. In the densest regions, dust becomes so thick that no light escapes. These areas appear completely opaque from the outside, dark even against the backdrop of space. But inside, particles collide more frequently. Hydrogen molecules gather in numbers so large they cannot be imagined on human scales. Over thousands of years, Gravity pulls them inward, creating a slowly contracting sphere that grows warmer and denser at its center. The earliest hints of a star begin here, hidden behind layers of dust. You drift closer to one of these cores, sensing the subtle warmth rising from within. Though the temperature is still cold by stellar standards, it is slightly higher than the surrounding cloud. The slow collapse continues. As the core shrinks, it begins to rotate, just as all collapsing structures do. This rotation flattens the surrounding material into a disk, swirling around the core like the early outlines of a solar system. Meanwhile, the core at the center continues to heat as gravity tightens its grip. This stage can last for millions of years. From the outside, nothing appears to change. The cloud remains dark, quiet, cold. But within the core, a protostar begins to form. It is shrouded by dense layers of dust and gas, glowing only in the infrared. You drift gently through the cloud, feeling the faint warmth of these hidden stars, embryonic lights still wrapped in their natal cocoons. They grow heavier as material from the surrounding disk spirals inward, adding mass in slow, steady streams. As time passes, the protostar grows hot enough to ignite nuclear fusion. The first sparks of starlight appear deep within the cloud, still too faint to break through the thick dust, but glowing with internal promise. The energy from fusion builds and builds until the pressure becomes too great. Suddenly, the protostar releases a burst of radiation strong enough to push back the surrounding material. Jets of gas shoot outward along the star's poles, carving narrow channels through the nebula. These jets travel for light years, glowing with soft blue light as they interact with the gas around them. You drift near one of these jets, watching it slice through the darkness like a slender beam. Shockwaves ripple through the cloud, compressing nearby material and sometimes triggering the formation of new stars. This is the beauty of star nurseries. Creation begets creation. One collapsing core can influence dozens of others, sending ripples through the molecular cloud that ignite new waves of formation. As the protostar stabilizes, its light begins to pierce the veil. The dust around it glows in reflection, illuminated by the first rays of its starlight. Over time, the cloud thins as stellar winds push away the remaining gas. The once hidden star emerges from its cocoon, shining brightly against the now translucent nebula. This process repeats across the entire cloud, with countless stars igniting and clearing their surroundings. What was once a dark patch becomes a region of brilliant color and light. Nebulae, like the Orion Nebula, show these regions in breathtaking detail. Imagine drifting through such a nebula now. Vast curtains of glowing gas stretch across your view, rippling gently in shades of pink, red, blue, and violet. Bright young stars cluster at the center, illuminating the cloud from within. Dust forms delicate shapes, pillars, arches, and ridges sculpted by radiation and gravity. The stars here are young and energetic, their ultraviolet light making the gas around them fluoresce like cosmic stained glass. Move closer to the pillars. These towering structures rise like cosmic mountains, each filled with dense knots of gas where new stars are forming. The light from nearby stars erodes the edges of the pillars, sculpting them slowly over time. Inside the darkest recesses lie the forming stars, hidden even from telescopes. As you drift into the shadow of one of these pillars, the light dims and the dust surrounds you like fog. Here is where gravity works most quietly, forming new cores that will soon ignite. The process of star formation is both delicate and powerful. It requires the perfect balance of density, temperature, and turbulence. Too much motion, and the cloud tears apart before stars can form. Too little, and gravity cannot overcome the gas's internal pressure. But when conditions align, the result is a burst of creation, an entire cluster of stars born in one region, some destined to live long, gentle lives, others to die in brilliant explosions. As you drift deeper into the nursery, you begin to see the early emergence of a new star cluster. These stars are young, hot, and bright. They illuminate their surroundings with intense blue light, heating the gas until it glows. The cluster contains stars of many sizes, arranged in loose orbits around their common birthplace. Some will drift away over millions of years, joining the broader population of the galaxy. Others will remain together for billions of years, held by their gravitational bonds. Imagine drifting above this newborn cluster, watching the light of thousands of stars shimmer through clouds of dust. The colors shift gently, blending into soft gradients of red, gold, and violet. In some areas, the gas is thin enough that distant stars shine through like glittering jewels. In other areas, the dust is so thick that it forms dark patches silhouetted against the glowing background. The elements created by older stars, carbon, oxygen, silicon, iron, now mix with hydrogen and helium in these clouds, forming the raw material for new worlds. In the disks around the newborn stars, grains of dust begin to collide and stick together, forming pebbles, then rocks, then mountains, then planet-sized bodies. Over millions of years, these bodies clear paths in the disk, becoming planets, moons, asteroids, and comets. Entire solar systems emerge from the swirling material, shaped by gravity and heated by the light of young stars. As you drift away from the nursery, the colors fade, and the silhouettes of dust clouds dissolve into the broader glow of the galaxy. The stars you watched being born will one day burn brightly, live through their own transformations, and eventually die, returning their elements to the cosmos. Their remnants will seed new clouds, new stars, new planets, and new possibilities. The cycle is endless. Stars are born, live, die, and give rise to new stars. Galaxies recycle their material, creating layers of generations stacked across billions of years. And with each cycle, the universe grows richer in complexity. Now, as you move away from the star nursery, the journey turns towards something deeply personal, something woven into your very being. For the elements created by countless stars, those forged in fusion, released in red giant breaths, and scattered by supernova explosions, have become part of you. Ahead lies a reflection on the profound truth that connects every living thing to the stars. You are made of stardust. Stardust and life. Drift now into a quieter region of space. The star nursery fades behind you, its glowing curtains dissolving into the distant haze of the Milky Way. What remains is a deeper stillness, a gentle quiet woven through darkness and soft pinpoints of starlight. Here, in this calm expanse, a profound truth emerges, one that threads through galaxies, stars, planets, and living beings. It is the truth that every atom in your body has seen the inside of a star. Float in this silence for a moment. Feel the calm stretch around you like a vast and endless night. In this stillness, imagine the atoms that make up your body. Atoms in your blood, in your bones, in your breath. Carbon, oxygen, nitrogen, calcium, iron. Trace each one back through time, back through the earth that formed them, back through the gas clouds where they drifted freely. back through the stars that forged them in their blazing hearts. Each atom carries a story older than Earth, older than the sun, older than life itself. The carbon in your cells was created in the core of a dying star during helium fusion. The oxygen in your lungs came from stars that fused carbon into heavier elements. The iron in your blood was forged in the last seconds of a supernova explosion, thrown into space with unimaginable force. Your body is a collection of stardust, matter that has been shaped, heated, fused, and scattered by countless generations of stars. Imagine drifting through a timeline of the universe. Begin with the earliest stars, the first massive giants that lit up the cosmos. These stars lived fast and died violently, scattering the first heavy elements into space. Their remnants mixed with hydrogen and helium gas, forming the next generation of stars. Those stars grew more complex, producing carbon, oxygen, neon, and magnesium. When they died, they released these elements into space. Across billions of years, this cycle repeated. Stars formed, lived, died, and released their elements into the galaxy. Each generation enriched the universe with heavier and more complex atoms. As you drift through cosmic time, imagine these atoms swirling through space, carried by winds, shockwaves, and gravity. They wander through nebulae, join molecular clouds, and eventually take part in forming new stars and planets. The cloud that formed our solar system was rich with elements created by long-dead stars. That cloud collapsed, spun, flattened, and became a disk. At its center, the sun ignited. Around it, planets formed. On one of those planets, water gathered. Organic molecules emerged. Life began. The atoms that now make up your body traveled through all of those stages. They drifted through the galaxy long before Earth existed. They were part of nebulae, part of stars, part of explosions, part of dust clouds. They were shaped by forces so immense and beautiful that the human mind can only grasp them in glimpses. Yet here you are, composed of those ancient materials, breathing with lungs filled by oxygen forged in stars, thinking with a brain powered by chemical reactions using atoms born billions of years ago. Imagine floating close to Earth now. Drift gently toward the blue glow of oceans, the soft white swirls of clouds, the warm greens and golds of forests and plains. Life has flourished here in countless forms. In the air, birds glide. In the water, fish weave their way through currents. On land, plants reach towards sunlight, and animals move through their habitats. Every living being carries the legacy of the stars. Every breath of air, every drop of water, every grain of soil is part of the cosmic cycle. Consider a single leaf on a tree. The carbon inside that leaf was created in a star during helium fusion. As the leaf absorbs sunlight, it uses that carbon to grow, creating sugars and fibers that feed its cells. When you breathe out carbon dioxide, you return some of that stardust back into the atmosphere, where the leaf absorbs it again. You are participating in a cosmic dialogue that has been going on since the beginning of time. Imagine a heartbeat. The iron in your blood pulsing through your veins is the same iron that once drifted through space after a supernova explosion. Iron carries oxygen throughout your body, enabling you to move, think, and feel. The iron atoms are still doing what they were made to do, bind with oxygen. They have simply changed where they do it. Drift now into the quiet of the ocean. Imagine the salty water brushing against your skin. Salt contains sodium and chlorine, both elements made long ago in stars that lived and died before the Earth formed. The calcium in your bones, the phosphorus in your DNA, the magnesium in your muscles. Each one has a stellar origin. You are not separate from the universe. You are woven into it, made from its ancient materials, animated by its energy, shaped by its long cosmic history. Move upward now, drifting into the atmosphere. The nitrogen that fills most of Earth's air was forged in stars through complex fusion cycles known as the CNO cycle. Reactions that transformed hydrogen into helium while creating nitrogen as a byproduct. Every breath you take is a gift from ancient stars. Every inhale and exhale is a continuation of the element's journey through time. Now drift into the soft darkness above the clouds, into the high glow of the atmosphere where day meets night. Look down at the Earth slowly turning. Look up at the stars scattered across the sky. Feel your connection to both. You are the meeting point between the Earth beneath you and the stars above you. Your body is Earth, atoms gathered from the soil, the water, the air, and your atoms are stardust, ancient, cosmic, universal. As you drift further outward, imagine that the universe is breathing in cycles of creation and transformation. Stars are born, stars live, stars die, and the universe reshapes itself through their light. Galaxies swirl in slow rotations, gathering dust and gas into spiraling arms. Nebulae expand and contract. Planets emerge and orbit their stars. Life arises, evolves, flourishes, and fades. Everything is part of a continuous, interconnected cycle. And you, quietly drifting now in the serene starlight, are part of that cycle. Your atoms are ancient. Consciousness, in this moment, is the newest expression of something deeply old, something woven from the fabric of the cosmos. When you gaze at the stars, you are gazing at your origins. When you breathe, you are breathing with the atoms of long-dead stars. When you live, you are carrying forward the legacy of the universe. The story of stardust is the story of belonging. It is the realization that you are not separate from the cosmos, but an expression of it. It is the gentle truth that everything in the universe is connected through cycles of light, gravity, and time. Now drift quietly back through space, feeling a deeper understanding settle inside you. Ahead lies the final chapter, a soft look at the long future of the universe. For even as stars are born today, the cosmos is changing. The number of newborn stars will decline. Galaxies will evolve, darkness will grow, and the distant future will unfold in silence. Ahead awaits the story of what the universe will become, the future sky. Drift now into a quieter era of cosmic time, farther than the eye can see, and deeper than the imagination usually wanders. The universe around you expands in gentle silence. Galaxies drift apart like glowing islands carried by a slow, unwavering tide. Stars burn in their steady rhythms. Nebulae shimmer softly in distant pockets. And yet, beneath the calm surface, time is carving a long path into the future. A path where the universe changes, ages, and moves toward its distant destiny. Imagine yourself suspended in this quiet cosmic moment. The Milky Way stretches beneath you like a river of starlight, its spiral arms glowing with blue clusters and golden regions of older stars. Beyond it, countless other galaxies flicker like lanterns scattered through an endless night. Some are small and hazy. Others are giant spirals or thick elliptical clouds. Each one carries billions of stars. Each one moves through space on its own slow arc. Now drift forward in time, gently, effortlessly, watching the universe evolve around you. Millions of years pass like a soft breath, then hundreds of millions, then billions, The changes are slow, graceful, and serene. Star formation, once common and vigorous, begins to decline. The molecular clouds that give birth to stars become rarer. The gas that fuels new creation grows thinner, having been consumed and transformed through countless cycles of star birth and death. The Milky Way still creates stars, but fewer than before. The once bright nurseries dim, and the great clouds fade into wisps that no longer collapse easily under gravity's pull. As the clock of cosmic time advances, galaxies begin their slow dances with one another. The Milky Way drifts ever closer to the Andromeda Galaxy, its large spiral twin. For billions of years, they have moved toward each other across empty space, drawn together by their mutual gravity. From your vantage point, you see them getting nearer, two great spirals stretching their arms across the void. Move forward another billion years. The galaxies grow so close that their stars begin to feel the pull of each other's gravity. From afar, you watch their shapes distort, their spiral arms stretching into delicate bridges of starlight. Stars are flung into new orbits. Gas clouds collide and compress, temporarily igniting a new but brief wave of star formation. The collision is slow by human standards, unfolding over hundreds of millions of years. But to you, drifting without the passage of days or nights, it unfolds with dreamlike beauty. Eventually, the two galaxies merge completely. Their spirals dissolve into one enormous elliptical shape. The new galaxy, sometimes called Milkomeda, glows with the combined light of 1 trillion stars. Yet, even in this luminous transformation, star formation continues to decline. Much of the gas has already been used. Much has been heated or flung into space during the merger. The new galaxy is beautiful, but quieter than before. Now drift farther into the future. The universe continues to expand, stretching space itself. The distance between galaxies grows larger. Light from faraway galaxies becomes more redshifted, stretched into longer and longer wavelengths. Eventually, many galaxies drift beyond the cosmic horizon. Their light becomes too faint to reach this part of the universe. From certain vantage points, the sky grows emptier. The universe feels larger, quieter, more spacious. Within galaxies, stars continue to live out their lives. Red dwarfs, with their astonishing longevity, shine quietly for trillions of years. These tiny stars become the primary lights in the universe's distant future. Their soft glow fills the galactic night with faint reddish warmth. Planets orbiting them continue to bask in steady light, though the universe around them grows darker. White dwarfs cool. Neutron stars remain where supernovae left them, spinning more slowly as eons pass. Black holes drift through the galaxy, silent, invisible, and patient. Some black holes merge with others, releasing bursts of gravitational waves that ripple through the fabric of space-time like soft tremors. These events echo in silence, detectable only through the vibrations they leave behind. Move farther still into the future. The last reservoirs of star-forming gas are used up. No new stars ignite. The galaxies become collections of aging stars and stellar remnants. The large, bright stars died long ago. Only red dwarfs remain, along with their quiet, cooling cousins. Trillions of years pass. The red dwarfs too begin to burn through their fuel. They dim slowly, turning from red to deep infrared, eventually becoming dark, invisible cinders. The universe grows colder. But this cold is not harsh. It is peaceful, like a long, quiet night settling gently over everything. White dwarfs have cooled into black dwarfs, cold lightless spheres of crystallized carbon and oxygen. Neutron stars cool as well, their inner heat slowly fading. Black holes remain dark sentinels in the cosmic night, the most enduring objects in a universe growing increasingly sparse. Even so, the cosmos is never truly still. Particles occasionally collide. Black holes slowly lose mass through Hawking radiation, over unimaginable timescales, far longer than the age of the universe today. Black holes evaporate. One by one, the giants fade, releasing their last whispers of energy as they disappear. What remains is a universe filled with faint, cold particles drifting in darkness. Space continues to expand. Galaxies have faded into dissociated stars, and then those stars faded into remnants, and those remnants into silence. The sky is no longer filled with points of light. It is a deep, infinite dark, stretching endlessly in every direction. And yet, even here, in the quietest future the universe can offer, there is beauty. A beauty not of brightness, but of understanding. A beauty woven into the very structure of reality. For everything that exists, every particle, every atom, every whisper of energy, is part of a cosmic story that began with the birth of stars and continued through their lives, their deaths, and the transformations they created. But as you drift in this future sky, another truth becomes clear. You do not need to travel trillions of years into the future to see the universe's beauty. You have seen it already, in the birth of stars, in their luminous lives, in their dramatic ends, in the clouds that rise from their ashes, in the particles that formed your body, in the light that traveled billions of years to reach your eyes. The story of the universe is written all around you, in the sky you see each night, in the atoms that make up your world, in the very breath you take. Float quietly now, returning from the distant future toward the present. The stars of today glow softly in the darkness. They shine with the same light that shaped your atoms, warmed your planet, and illuminated your world. They are ancient, yet still young in the vast timeline of the cosmos. Their light reaches you as a reminder of everything that has come before and everything that awaits in the quiet future. In this moment, as you drift beneath the stars of the present, a deep sense of calm settles. The universe has lived long before you, and it will continue long after. Yet for this moment, you are here, a living, breathing part of the cosmic story, a collection of stardust, a witness to the sky, a fragment of the universe experiencing itself. And now, gently, the journey through the life and death of stars draws to a peaceful close. Closing reflections. Settle now into the quiet space between breaths, floating gently through a cosmos that feels softer, calmer, and more familiar than ever. The long journey through the birth and death of stars has brought you across the universe and back again. You have drifted through darkness and nebulae, witnessed the gentle glow of newborn stars and the brilliant fury of supernovae. You have watched neutron stars spin like cosmic beacons, felt the pull of black holes bending time itself, and traced the quiet, crystalline coolness of white dwarfs. You have traveled through star nurseries where new light awakens, and you have followed atoms as they journeyed from ancient suns into your own body. Now, in this final stretch of the story, the universe invites you to rest within its vastness. Imagine yourself floating beneath a night sky untouched by artificial lights, somewhere distant and peaceful. The air is cool, steady, and still. Above you, countless stars glow with a soft and timeless clarity. Their light travels through the darkness like quiet messages written across time. Each star is a reminder of the journey you have taken, a small beacon carrying the memory of cosmic creation. Breathe deeply now. Feel the calm of the universe settle over you like a warm blanket. The stars do not rush. They do not strain. They shine in long, patient rhythms, illuminating the darkness with a gentle and constant presence. Their lives unfold across billions of years, and yet their light reaches you effortlessly, touching your eyes, your thoughts, your breath. In this moment, imagine the story of the universe not as something distant and unreachable, but as something you are part of, woven into from the very beginning. The hydrogen that fills the stars was formed moments after the Big Bang. The elements coursing through your body were forged in the furnaces of long-dead stars. The oxygen you breathe was shaped in stellar cores. The iron in your blood came from supernova explosions. The calcium in your bones was once part of a nebula. You are connected to the past of the universe in a direct and literal way. Let that understanding settle gently into your mind. Feel its weight and feel its softness. You are made of the universe, and the universe is made of you. As you drift through this final reflection, imagine the stars you have witnessed through this journey as companions, rather than distant strangers. Each one tells a story. Each one lived a life. Each one contributed to the galaxy in its own quiet or dramatic way. The stars are not distant ornaments decorating the sky. They are ancestors. They are the sources of light, heat, and matter that made everything possible. Imagine the first stars, massive and bright, igniting in the early universe. Their light cut through the darkness like the first sparks of awareness. Their deaths filled space with heavy elements, enriching the universe with the materials that would one day form planets. Then imagine the next generations, forming in nebulae of vibrant color, stars of all sizes, shapes, and intensities, each following its own path through the cosmos. Some stars lived long, steady lives. Some lived fast and burned intensely. Some ended in gentle fades. Others erupted in colossal explosions. And yet, each star, no matter how large or small, contributed something essential to the universe's story. Now imagine yourself floating through a quiet region of space. There is no noise here, no urgency, only the soft hum of cosmic background radiation and the light of distant galaxies drifting across the darkness. Every direction you look reveals the deep, tranquil beauty of creation. The Milky Way arcs overhead, a soft river of stars stretching from horizon to horizon. Clusters sparkle like jewels. Nebulae glow in delicate pastels. A few faint meteors streak across the sky, reminders of the small pieces of cosmic material drifting through Earth's atmosphere. Somewhere far beyond, black holes curve space like invisible sculptures. Neutron stars pulse in steady rhythms. White dwarfs cool like fading embers, and new stars ignite in hidden cradles of dust. Each process continues without hurry. Each moment unfolds without rush. The universe moves with a rhythm that is patient, steady, and enduring. Allow your mind to follow that rhythm. Slow your thoughts. Soften your breath. Let your awareness expand gently, like a wave drifting outward across still water. You are floating in the great calm of the cosmos now, supported by the same laws that guide every star and every atom. The force that shapes galaxies also shapes the curve of your breath. The gravity that draws stars together also holds your feet to the ground when you walk. The energy radiated by stars warms the earth and nourishes life. You are part of this system, embedded within it, connected to it, not by metaphor, but by substance. Allow that understanding to wrap around you, comforting and grounding. Imagine that, with each breath you take, you draw in not just air, but the memory of stars. With each exhale, you release part of yourself into the world, just as stars release their light into space. The cycle continues, effortlessly and naturally. You are not separate from the universe. You are the universe, experiencing itself for a moment through the lens of a human life. The stars above you shimmer softly. They seem to breathe with you, expanding and contracting in gentle waves of light. Their glow feels like a whisper, a quiet reassurance that everything in the cosmos, from the grandest supernova to the smallest atom, is part of one magnificent whole. Let your consciousness drift now into a sense of unity, into a feeling that you are connected to everything and that everything is connected to you. There is no need for worry here, no need for tension. The stars do not worry. The galaxies do not rush. Time unfolds at its own pace, and you are allowed to rest within it. Allow your thoughts to soften. Allow your mind to settle. Allow your body to feel supported by the quiet of the night, as if you are floating in the gentle cradle of starlight. Feel the warmth of your existence, the calm that surrounds you, the stillness that fills the universe. You have traveled through the full cycle of starlight, from the darkness before the first stars to the future sky far beyond human imagining. You have witnessed creation, destruction, renewal, and transformation. All these processes mirror the cycles within your own life: beginnings, changes, endings, and new beginnings. Now rest in the knowledge that you are part of this cosmic rhythm. Rest in the understanding that your presence is woven into the story of the stars. Rest in the quiet embrace of the universe. As the journey comes to a close, the stars shimmer softly above you, ancient and patient, guiding you into a deep and peaceful stillness. The universe continues its slow dance, and you drift gently within it, calm, relaxed, and serene. Let the night sky hold you now. Let the starlight ease you into rest. Let the cosmos cradle your mind as you drift further into quiet, gentle sleep.